and less solar energy, and the temperature would go down, and you'd reinforce the downward trend. The thing that makes it positive is that it reinforces whichever trend occurred. But in the context of a warming planet, the initial change is a warming. That's what's happening now. And so the Arctic amplifies that change with positive feedback. Here's a negative feedback. It's called cloud albedo feedback, another feedback involving reflectivity. Here's Earth's temperature. Again, if there's an initial increase, that increases the amount of evaporation, and that increases the amount of clouds that form. But clouds are reflective. They reflect a lot of sunlight into space. And so the albedo, the reflectivity, increases, and therefore the amount of sunlight that gets absorbed goes down, and therefore the Earth's temperature decreases. So an initial increase is countered by this decrease. That's a negative feedback. And the climate system is full of those feedbacks, and to understand the climate system, we need to understand feedbacks. One of Hanson's big points in the paper that leads to 350, and again, I'm saying this to all of you who are out there marching with 350.org stickers and all that kind of stuff, this is where the 350 is coming from. There are two kinds of feedbacks. There are fast feedbacks. They occur on short time scales of days to years. Something happens, and within a few days to a few years, something changes as a result. For example, it gets a little warmer, and more water evaporates, and almost immediately there's more water vapor in the atmosphere. And water itself is a greenhouse gas, and so immediately there's an amplification of that warming within days. Water vapor feedback, that's one example. That's the one I just described. Some other examples, clouds. They form quickly. Sea ice is relatively fast, on the order of timescales of months or years to respond to changes in climate. Aerosols, particles that go in the atmosphere coming off the ocean and other coming off sandstorms on the desert and stuff. They're fast feedbacks. But there are also slow feedbacks. And one of the big points of Hanson's paper is to talk about slow feedbacks and get you to understand that they are really important over the longer scale and that we haven't been thinking about them enough. And they include, they're things that occur on centuries and longer time scales, and they include, particularly in Hanson's paper, the big bad one is ice sheet disintegration. He's really worried about that. That's something that takes many years, decades, centuries to respond to climate change. Vegetation changes that follow deglaciation, follow new land being exposed where there was previously ice. Those are examples of slow feedbacks that occur on very long time scales. Okay, so those are my 5 science concepts, and now I want to look quickly at the one other thing we need to understand before we look at Hanson's paper, and that is, one more very long geological weathering. That's too long for us to worry about, because that's on millions of year time scale. I want to talk briefly about how it is we understand paleoclimate, because Hanson's 350 paper is based very, very strongly on the climate of the last million years. So how do we measure that? And it even has a strong component of dependence on the climate of the last 65 million years. So I've got to give you a little nuclear physics. Okay? There are elements. And elements contain in their nuclei contain protons and neutrons, and protons are electrically positive, and the number of protons determines what element you are. So if you're carbon, how many protons have you got? 6. If you're oxygen, how many protons have you got? 8. If you're hydrogen, you got 1. If you're helium, you got 2. If you're uranium, you got 92, etc. But you can have different numbers of neutrons because they don't affect your electrical charge, and so they don't affect what element you are. And in fact, hydrogen comes in the common isotope H1, the isotope H2, deuterium, which has a proton and a neutron. Hydrogen just has, H1 has a proton. About 1 out of every 6,500 hydrogens is that. There's also a third isotope. What's its name? Everybody in this room knows right now. Tritium. We hear that word every day in the papers. The stuff that's leaking out of Vermont Yankee, that's 1 proton and 2 neutrons, and that's unstable, which is why it's radioactive. But those two are both stable. They can both exist forever. Oxygen comes, most of it is oxygen 16, but some of it, a little tiny fraction of it, is oxygen 18. And the heavier isotopes are a little bit heavier. They're identical chemically, but they're a little bit different physically because they're a little bit heavier. And that allows us to use them as a thermometer. Here's how we do that. Most oxygen is O16. 8 protons, 8 neutrons. Some of it is O18, only about 0.2%. 8 protons still because it's oxygen, but 10 neutrons. And water containing the lighter isotope can evaporate a little more easily because the molecules are moving a little faster. They're easier to break through the surface tension at the surface of water. They leave atmospheric water vapor depleted in oxygen 18. So the water vapor in the atmosphere has less O18 than the stuff in the oceans. That water generally evaporates in the tropical regions where it's warmer, it moves northward, it precipitates out, and the Arctic and Antarctic precipitation ends up, depletion depends on the temperature. And consequently, to make a long story short, if you look in ice cores, which contain trapped air bubbles, which contain oxygen 18, or actually those contain carbon dioxide. You look right in the precipitation itself in the water that formed the ice and snow. You can measure the amount of depletion of this heavy oxygen isotope quite accurately, and you have, as a result, a thermometer. And if you have ice cores that you can date, and often you can because you get layers for every year, or maybe sometimes you get more mushy layers, but they span a few decades, you can time what the temperature was at different times back. You can do the same, and so these annual layers form a datable record of the temperature at the time the ice fell, and you can do the same thing with hydrogen isotopes. So we have a paleothermometer that we can use to reconstruct climate in any region where we can get an ice core, and we can date the ages of the ice in that ice core. We can also get out of those ice cores where there are trapped bubbles the greenhouse gas concentrations. So we've got a way to reconstruct paleoclimates. And to give you an example, this is a very famous ice core from the Vostok, the Russian Vostok station in Antarctica. It goes back 420,000 years. It's all available to you from the Carbon Dioxide Information Analysis Center if you want to play with this data. It shows this very strikingly regular pattern of about 100,000-year intervals. It's relatively cool for most of that time. There is a brief 10 to 20 to 30,000 year spike of warmer climate. That's the interglacial period. So we have the interglacials. We're in an interglacial right now. Hanson claims we humans have inexorably altered this pattern and we will never have an ice age again. But those are the interglacials. There are these relatively short warm periods. Again, they're occurring about every 100,000 years, and they're punctuated by the ice ages, and there's a difference of about 10 degrees Celsius in the Arctic and Antarctic temperatures between the ice ages and the interglacials, and we're in one of these interglacials right now, and maybe nearing the end of it, or should have been. Because we also have carbon dioxide measurements from air bubbles trapped in these ice cores, we can also plot the carbon dioxide concentration. And whoa, what a correlation. Now, I could give you a whole other lecture on why there are ice ages. You can ask me about that in the question period. And I can give you a whole other lecture about the complexities in this correlation, which are not quite as simple as they might seem. But the main point is there is just an utterly clear correlation between, when the carbon dioxide is high, so is the level of temperature, and vice versa. Yeah?
Are the data sensitive enough to tell which came first?
Yes. That is a good question. And the temperature rise generally precedes the CO2 rise by a few hundred years. And in fact, there's an article in the current issue of Nature about an attempt to pin that down with a better ice core that they're drilling at the top of a ridge in Antarctica on a divide between ice that flows two different ways so that the ice won't have moved and smeared itself out, and they're going to try to get higher resolution answers to that question. But and a lot of, by the way, a lot of greenhouse skeptics will jump on that fact and say, look, the temperature rose first, so it can't be caused by carbon dioxide. It's much more complicated than that, and I'll say a little bit about that, but not much. By the way, here's the CO2 scale. Notice that pre-industrial CO2 was about what level? You 350ers all ought to know this number. Where were we pre-industrial? About where? About 280 or so, right? Where are we today? 385, 390. There's where we are today. I just point that out. This is not part of my talk on Hanson to show you that. But that's where we are today. And I just want to point out, if you don't think we humans have done something dramatic to the climate system, today's level of CO2 is higher by a huge amount than anything the planet has seen in the last 420,000 years. We know now from another ice core project that's higher than anything we've seen in 1 million years, and we know, in fact, that it's higher than anything the planet has seen probably in 20 million years. We're not as sure of that, but it's big. It's a big change. We humans have done something dramatic to the atmosphere. Now, someone had a question, and I ignored it. Who had a question? Bob.
I was just going to ask what you thought of the Rudderman hypothesis.
Ah, yeah, Bill Rudderman. I just had a conversation. The question was, what do I think about Bill Rudderman's hypothesis? I won't spend a lot of time on that right now, but I'll just say what it is. Bill Rudderman is a climate scientist from the University of Virginia, and he believes that humans, starting about 8,000 to 5,000 years ago, with agriculture, actually began releasing enough greenhouse gases to prevent what would have been a fairly gradual but still noticeable slide into the next ice age. He thinks that hypothesis, I think, has been largely discredited, but not entirely. Yeah, I just had an email exchange with Bill about a week ago, and not on that question, but another one. So So moving on. So here's a review. Here's all our science concepts. So if I were to give a quiz right now, you would all be able to describe these. Okay? So we need to have all this under our belt in order now to understand the Hanson paper, which won't take long now that we have all the science behind us. Okay? So what do Hanson et al. Do in their approach to 350? The first thing they do is they confirm that the fast feedback climate sensitivity is about 0.75 degrees C per watt per square meter, about 3 degrees for a doubling of CO2. And by the way, Hanson points out that's a number that was arrived at in the 1970s, and despite all the climate research that's going on since then, that number hasn't really changed much. So they confirm, first of all, using some paleoclimate studies, that the fast feedback sensitivity that everyone talks about 0.75 degrees C per watt per square meter, about 3 degrees C for a doubling of CO2 is probably right. Then they incorporate slow feedbacks. And the way they do that is to look at that Vostok temperature record I showed you. Remember, it varied about 10 degrees between Ice Age and warm interglacial period? They cut that number in half because they say that's the Arctic and Antarctic temperature variation, and we know that there is this amplification due largely to ice albedo feedback effects that makes the temperature changes in the Arctic and Antarctic about twice the global average. So they divide that in half, and to get the global temperature variation as about half that of the Vostok temperature variation. I'm using physicsy terminology. Delta means a change in, so that's a change in temperature. So they take the global temperature variation, delta T global, as about half that for this Vostok ice core from Antarctica. They look at the greenhouse gas forcing from the Vostok record. All the greenhouse gases, carbon dioxide as I showed you, but methane and others are also available there. They then plot these on a graph, and they cleverly scale the graphs. Remember I showed you those two plots and they correlated. They went together. Well, they did more than that. They plotted them on the same graph, and they made the scales of the graph so that those two would sit right on top of each other. And they concluded that there is a slow feedback climate sensitivity that is twice what the fast feedback sensitivity is. That the climate is twice as sensitive as people who had ignored these slow feedbacks had thought. It's about 6 degrees Celsius for a doubling of CO2. That's one of the biggest, most important conclusions from the 350 paper. You know, 350, as Bill McKibben says, may be the most important number on the planet. But part of where 350 is coming from is 6 degrees C rather than 3 for a doubling of CO2. Question? Black carbon is something people worry about in this. And I think this particular analysis is not. The black carbon is in the fast feedback stuff. What I'm about to show you is looking just at the slow stuff, and so it ignores that. That's a good, black carbon is an important process. We can talk about that more. So here is their graph, and what they've done is arrange these scales so the zeros are in the same place. The axes have been scaled. This is not cheating. It's not doing a trick or something. It's just doing some math to put these curves as close to on top of each other as they can. And let's look at this in a little more detail. So on the left, we see the temperature deviation from pre-industrial. So 0 is pre-industrial. Anything bigger is warmer than pre-industrial. Anything below is cooler than pre-industrial. On the right, we have the axis for the effective forcing in watts per square meter due to greenhouse gases. That's the green curve. The black curve is all forcings, which includes your black carbon, includes aerosols, includes volcanic eruptions, which are these big negative excursions, and so on. Includes a lot of stuff. All forcings. The green is just greenhouse gas forcings. The red is that half the Vostok temperature, supposed to represent the global temperature, and so on. Okay? Here's the point I want to make. If you have done all this scaling, then 3 degrees Celsius temperature anomaly happens when you have 2 watts per square meter of forcing. That's where you get the 1.5 watts per square meter, 1.5 degrees per watt per square meter. Doubling CO2 is 4 watts per square meter. Multiply 1 watt per square meter by 4, multiply 1.5 by 4, you get 6. That's where you get the 6 degree temperature rise for a doubling of CO2. It comes out of this curve. This is the most important curve in the Hanson 350 paper. You 350ers who really want to know what 350 is about, put this on your placards too and march around with it. Okay? Notice the scale comparison. I just said 2 watts corresponds to 3 degrees Celsius. That gives you a climate sensitivity of 1.5 degrees C per watt per square meter, or 6 degrees C for a doubling of CO2. That's where that comes from. Now, we haven't got to 350 yet, but we're getting close now. Notice that there is an expanded scale for the industrial era here. And notice that in the expanded scale, the effective forcing, the greenhouse forcing deviates from the from the total forcing, that's because we're putting a lot of aerosol pollution in the atmosphere, which causes a cooling effect and causes the overall forcing to be less than the greenhouse gas forcing alone. That's going to be important in just a minute. Okay? So how do we get to 350? Well, several ways. First of all, I'm going to do a crude calculation that is not in the Hanson paper. It's what I asked my final exam students to do. And it isn't quite right, because Hanson doesn't quite believe in the number I'm going to come up with. If you look at pre-industrial, that was 280 parts per million. If you double it, you got an increase of 280 parts per million. Hanson said in 2007, we don't want the temperature to go up more than 1.7 degrees. That implies a maximum CO2 increase. You see, that CO2 increase gives you 6 degrees. Double CO2, you get 6 degrees. Go from 280 to 560, add another 280, you get 6 degrees. So that says the most we can do if we want 1.7 degrees is we want 1.7 out of 6 of that 280. That's about 80 parts per million. Add that to 280 parts per million, and the maximum acceptable would be about 360. So that says if you want to hold the temperature rise to 1.7 degrees, which now Hanson says is too high, you better not go above 360. So that's a way of getting at a number close to 360. Hanson doesn't, as I point out, he didn't do that calculation. He doesn't do quite as mathematical a calculation. He gets there by energy imbalance, first of all. He says today's energy imbalance is somewhere in the range of 0.5 to 1 watt per square meter. IPC says something else, but Hanson says that. The forcing for a doubled CO2 is an additional 280 parts per million. That corresponds, we know, to 4 watts per square meter of forcing. He argues 4 watts per square meter, 280 parts per million means 1 watt per square meter corresponds to 70 parts per million. This is all, 9th grade algebra at most, so don't be scared by it. You want to eliminate a half a watt per square meter imbalance. Hanson says that's sort of the minimum imbalance we have. The minimum thing we want to do is get the Earth back in balance. How would we eliminate half a watt per square meter? Well, 1 watt per square meter is 70 parts per million. Half a watt is 35 parts per million. We better get rid of 35 parts per million of CO2 in the atmosphere. We're now at about 385 or 390. Take away 35, magic, you get 350. There's one place that 350 comes from out of this. Get the planet back in energy balance. Some other issues. We want to maintain the current climate zones. And here Hanson now get a little less quantitative. Civilization is adapted to the climate zones of the Holocene. He notices that climate zones are already shifting, and rapidly. Climate zones are shifting northward at about 6 kilometers per decade. So he concludes the present level is already deleterious. Another argument for some number below 385. Mountain glaciers. Present glacier retreat and warming in the pipeline indicate that's already a threat. Sea level rise. Equilibrium sea level rise for today's CO2. If you look at how much ice that would melt if we went there for a long time with that 6 degrees for a doubling of CO2 kind of sensitivity, we're going to go several meters higher in sea level. 10, 20 feet. That's a lot. He suggests 350. Coral reefs and ocean acidification are happening. 300 to 350 parts per million would relieve both these stresses on the ocean. So there's some other ways Hanson gets to 350, and he suggests an initial target of 350 parts per million. Now let me say a little bit about this term warming in the pipeline, and we're going to wrap up in the next 5 minutes or so. First of all, notice, back to this graph again. Here's the temperature deviation from pre-industrial. Here's the effective forcing. Hanson has plotted this cleverly so those curves lie right on top of each other. And what that means is the long-term temperature and forcing plots are identical, basically. In the long term, when you take all those long-term feedbacks into account. Now over here, the temperature curve, which is this purple curve, these are the actual measured global temperatures with that sort of sharp upturn that's happened near the end of the 20th century and into the 21st. He says that is the response to short-term feedbacks, but not to long-term feedbacks. The response to long-term feedbacks is identically the forcing curve, because these curves have been made to sit on top of each other. And there's the forcing curve. And there is about 1.5 to, well, that's watts per square meter, but if you look at that in terms of temperature, today's temperature is here. Today's forcing is about here. And that says that in the long term, we have about 2 degrees more warming that would occur just because of what we've done already. If we stopped emitting more CO2 into the atmosphere right now, we can expect about 2 degrees more warming in the long term. 2 degrees over what we've already got way above any 2 degrees above pre-industrial or 1.7 degrees above pre-industrial or whatever. That's where the warming in the pipeline comes from. Finally, Hanson goes back further with more indirect measures than we can get from ice cores, because we can't go back this far. In the Cenozoic era, we go back about 65.5 million years. We do get some oxygen-18 measurements from sediments on the sea floor. I won't go into the details. We know that Antarctic ice sheets began forming about 35 million years ago. This is million years before present. Northern Hemisphere ice sheets only started forming less than 10 million years ago. We are pretty sure that CO2 peaked at somewhere between 1,000 and 2,000 parts per million at that warmest period 55 million years ago. We think it's just pre-industrial ice age conditions, not pre-industrial, but in the bottom of the ice age was about 180 parts per million. And we're pretty sure at 35 million years ago, at the time of Antarctic glaciation, the time that ice first began forming, big ice sheets formed on the planet, it was about 450 parts per million. So from this, Hanson concludes that in the long term, 450 parts per million is enough to deglaciate Antarctica and make an ice-free planet. That's why 450 for Hanson is way, way too high, because in the long term, that results in an ice-free planet, and in an ice-free planet, we have about 75 meters worth of sea level rise, about 250 feet of sea level rise. And if you don't think that's a problem, Lake Champlain is at 95 feet, so you're submerged under that scenario right here. Timescale is centuries. On the other hand, Hanson is worried that positive feedbacks may cause that to happen sooner. Hanson is a big one on this idea of tipping points. These are nonlinear responses. A nonlinear response is when you change something, in this case the forcing of the climate, and gradually you change it and get a little response, temperature change or whatever, and then suddenly with almost no more change in force you get something nonlinear happening, something sudden jump. That's what he means by nonlinear response. And Hanson in this paper now identifies two things about tipping. There's a tipping level. He says if you maintain this forcing for a long time, you're going to get this consequence. And he can get some insights into that from paleoclimate. Then he talks about points of no return, where even if you reduce the forcing, even if you sucked carbon dioxide out of the atmosphere, you've gone too far and the change is inevitable. He says that's very hard to assess, but he says you can avoid that even if you temporarily exceed the tipping level. And that better be good news, because we're already at 385 and Hanson claims we need to be at 350. So it's a good thing that we're allowed to exceed those levels temporarily. The problem is what's temporary, we don't really know. The quantitative tolerance to this overshooting of these limits is just plain unclear. And for Hanson, in this paper and in his new book, the great big danger is irreversible ice sheet disintegration, which he thinks could occur much more rapidly than we've been led to believe. Is there a consensus about 350? I'm kind of out of time. This is sociology, so I won't go into it. Just some names of people who have talked about consensuses. I do want to mention one alternative that's come out since Hanson's paper, and it's this idea that was published in last April 30th Nature, the idea that it's less important to set levels of carbon dioxide and more important to talk about the total amount of carbon humanity is allowed to emit into the atmosphere. And these writers conclude that we better not emit more than 1 trillion tons into the atmosphere, and we've already emitted 500 billion tons. It doesn't really matter, they claim, and they show some graphs to kind of prove it, it doesn't really matter exactly how we emit the rest and what levels we reach. It's just if we emit more than 1 trillion tons total, we're going to be in trouble. And the dashed lines here show that responses to scenarios where you fix a level, in this case it was 490 parts per million, versus emitting a certain amount, and these red curves and some of the curves around them are about 1 trillion tons total. So there's an alternative to 350 parts per million, and I guess if it were me marching, I'd say 1 trillion tons, no more! But that isn't as jazzy as 350.org, so we'll go with that. Are there solutions? Hanson's solution is phase out coal by 2030. We've got to do that. If we do that, we'll peak our CO2 at about 400 parts per million. We have to draw down the carbon dioxide that's there already. We can do it with agriculture and forestry. He thinks we can get 60 parts per million out of changes in those practices. He thinks we can get about 8 parts per million with biochar, absorbing, sequestering carbon in the soils. If we burn biofuels, and not only burn biofuels, but also sequester their carbon, so we're taking additional carbon out of the system than would have been there, we can get down further. We can grow these on marginal or degraded lands, not competing with food. Coal is the biggie. There's 1 trillion tons of carbon in coal left in the world. Still left. These are by continent and country. I won't go into this in detail. Last graph I want to show you, and then I'm going to wrap up. this is from a talk I heard at the AGU meeting the year after I heard Hanson's 350 talk. And this is a very sobering result. This is based on some work by Ken Caldera at Stanford. And their question was, what if we continued business as usual? When would the planet's temperature have risen by 2 degrees? And they calculate it happens about 2045. Now, what if instead we did a really bad thing? What if we took and stopped burning petroleum fuels, oil, natural gas, stuff like that, and instead made those fuels from coal? What a terrible thing to do, but made synthetic fuels from coal. Well, coal is so bad, it's got so much more carbon, that in fact the time would be earlier. It would be 3 years earlier. And then they say, what if we don't burn any petroleum, and we replace all the petroleum fuels, all the fuels in our cars and trucks and airplanes, with synthetic fuels like hydrogen made from photovoltaics and wind, the things we environmentalists love? When would the temperature reach 2 degrees Celsius rise? Well, it would be a few years later. And the point is, oil doesn't matter. All of you driving Priuses, it's a great thing, I'm glad you're doing it, but it doesn't make much difference. All of us who are re-insulating our houses to save on heating oil, great thing to do. It's going to save you money, it's going to put less carbon, but nothing matters. Oil is a second-order effect, as we scientists say. What matters is coal. Hanson claims that if you use all these solutions he talks about, we will peak at somewhere over 400, maybe just over 400 parts per million, depending on which of these things we put into play. But if we stop burning coal, or don't stop burning coal, but stop emitting carbon from coal, we can sequester carbon from coal. If we do all that, we will be able to get down toward the end of the century, depending on which of these paths we take, down below 350. Okay? So Hanson et al.'s takeaway message is this. The goal for Hanson and colleagues is 350 parts per million. It's okay to overshoot that in the short term. What's short term? We don't really know quantitatively. We suggest an initial objective of reducing the 350 target to be adjusted as our scientific understanding and empirical evidence of climate effects accumulate. No coal emissions. Phase out coal emissions by 2030. You have to do that. You cannot burn all the coal reserves that are in the ground or we have climate disaster. Coal burning is okay with carbon capture and storage. The difficult task, the most difficult task, this phase out of coal that doesn't capture CO2 is Herculean, he says, but it's feasible compared with the efforts that went into World War II. No coal. And that's where I'm going to end. Thank you.